All right, section 6, chapter 6, section 4. And we're learning about work. First of all, what is the definition of work? From math or science, the definition is a force times the distance that force causes something to move. For example, if you were shoveling dirt out of a hole, you have to apply a force to the shovel to lift the dirt up, and the distance is how high you're lifting that dirt. That's a simplified. There's lots of other stuff in there that make it a much more complicated scenario than that. So then the question is, what is force? And when I ask that to the class, I always get, well, it's mass times acceleration. Or F equals m times a. So then I asked, what is mass? And that's something that students have trouble understanding. And often we hear the word weight show up. But mass is not weight. And the word density shows up. So I want to go through and help make sure that you understand the relationship between all these different quantities before we jump in and doing calculus with them. So every person's body is made up of mostly water, but a lot of different molecules, atoms, protons, neutrons, electrons, all that kind of stuff. That's matter. And the amount of matter is called the mass. So, mass in the metric system is measured in grams, or some multiple of it like kilograms, or micrograms, or milligrams, or something like that. That's what mass is measured in. Now, in the English system, most of you do not know what mass is measured in, but you do know what weight is measured in. And weight in the English is measured in pounds and perhaps ounces. And there might be some other units here, but that's the idea. So when you get on the scale and you say, oh, I am so many pounds and I'm so many kilograms, that's a misnomer. This is a measurement of your mass. This is a measurement of your weight. What is the measurement of weight? Well, if you are standing on the earth, your molecules are attracted to the Earth's molecules by what's known as gravity. And gravity, this attractive pull is called a force. And you could put a scale in here and measure how hard gravity's pulling you towards its mass, how much the Earth's mass and your mass are attracted. The scale holds you apart and says, oh, you're pulling on that, whatever. That force of attraction, that pull, is called weight. Mass is just the matter that makes you up, or the matter that makes up the Earth, or whatever planet you're standing on. Or the other person standing next to you. Their mass attracts your mass. You are pulled together by a slight force. It's the same force that pulls these together, except the Earth is so much bigger than the other body that you're pulled way more towards the center of the Earth than you are to that body. So weight is a force. It's measured in pounds in the English system. And in the metric system, you have to take the mass times the acceleration due to gravity, and that gives you the force in the metric system, and mass times acceleration due to gravity in meters per second squared is a Newton. And gravity in the metric system is 9.8 meters per second squared. So a Newton is a kilogram meter per second squared. But that's how weight should be measured in the metric system, not by mass, not by kilograms, which the scales often tell you. Now, why that's kind of important and how these are different, you can get on the scale and it'll say so many pounds, and the scale will say so many kilograms. Now, if you go climb up to the top of Everest and stand on that same scale, you're going to be further away from the center of the Earth, and so the force of attraction decreases, and you'll be a different amount of pounds, but the molecules that make you up should be the same, and so your mass stays the same. If you go from the Earth to a orbiting satellite like the space station, your mass stays the same. The amount of atoms, molecules, whatever that make you up stays roughly the same, but their two masses are further apart, and so therefore the gravitational pull is less, and so the forces change, but the masses don't. So what is a mass unit in the English system? Well, there's several. One of them is called a slug, and I just want to clarify that that's not the creature that slimes along the ground. A slug they're talking about here is like the bullet from an old musket, the lead ball that's shot out of a musket at somebody. Okay? So they were used to compare on a scale the two different masses and say, okay, that has a mass of such and such. Okay, so density is saying how much matter there is inside a volume. Mass per volume. However, you can have other kinds of density like mass per distance, just a distance x, if you've got it staying the same density as you move along. Then the cross-sectional area would be the same all the time, so times an x, if it's so much mass per in a cross-sectional area, then all you have to do is multiply by how far down you go to get the density. So density in normal definition is just how much mass in the volume. Now, if you've got a uniform rod, how could the density vary? In real life, how could it vary? Well, how can it be, let's say, heavy on this end will have a higher mass and less mass down here? Well, if it's a metal rod of some sort, the type of metal here has to have the molecules, packed more closely together than down here for this to be more dense than this. So you might have a rod that's maybe iron here or lead here that changes to steel or aluminum or whatever. So it's got a varying consistency. That would make one end heavy and one end light. If it was made up of wood, you might have a heavy oak connected to balsam or something like that. But getting the same amount of mass in the different masses in the same volume is what it would mean to go from a big density to low density, or low density to high density. So that's my spiel on these. Now, so let's now try doing a problem. Now, this is stuff I did Friday. So let's say we start off with a tank of water. And it's filled up to 4 meters deep. The radius is 2 meters and the height is 5 meters. And the water's up to that level. And we need to lift the water out of the tank. So we put a hose in here, and we have to raise it to the top of the tank. Now, since the water comes up back up the hose, all we're doing is lifting the water from the height that the water level is to the top of the tank. So I'm going to take a thin slice right off the top, and since it's up and down, I could call it dy, but I'll call it dx. And so if it's a circular tank, radius 2 meters, the volume of this slice of water would be pi r squared h, but the h would be dx. The r would be 2 meters quantity squared. So it's 2 meters times 2 meters times the thickness, which is in meters, times pi. So that's a volume. If you take volume times the density of water, you will get the mass. Volume times density gets you mass. So let's get the mass. So now we have to take the density of water, and the density of water, we usually like to, if we're doing it, in the metric system, we usually like to talk, well, density in chemistry, whatever, is mass per cubic centimeter, per milliliter, cubic centimeter. But in these kind of problems, we want to deal with a bigger unit, so we're going to have mass, kilograms per meter cubed. Now to do that, because these are all meters and not centimeters, since water is kind of a standard for mass, if it's a liter, which is 10 centimeters by 10 centimeters by 10 centimeter block, which means there's 1,000 cubic centimeters make a liter. And to make a meter, we'd have to do 10 of these across, 10 back, and 10 high. So it'd be thousands of these. So there's 1,000 cc's in this, but that we don't need to know that. There are thousands of 1,000 of these that make a cubic meter, and so there's 1,000 kilograms in 1 meter cubed of water. Now, oil would be a less dense. It would be more like 800 kilometers in a meter cubed, etc. So this is the volume of that slice times its density, which is 1,000 kilograms per meter cubed. So the meter of the dx and the meters that are getting squared here cancel the meters cubed, and we get kilograms, which would be the mass. And a force is mass times acceleration, so we have to take it up here, Force is mass times acceleration, so we have to take the mass, all of this stuff, times the acceleration. Due to gravity, it's 9.8 in the metric system, meters per second squared. And so we'd get, that makes a Newton. And then we have to take that, so that makes the force. We finally have got the force. We have to take it times the distance we're lifting it. Well, this piece of chunk of water, if we call this distance x, then we have to lift that slice of water x to get it out of the top. And then the next slice down would be lifted the new x, and the x is going to change from 1 to 5. And so we'd want to add up all these masses from 1 to 5 of this. And there's the dx, which I moved to the end. So let's clean this up here. The work done to get the water out of this tank, at least lifted to the top of the tank, would be integral from 1 to 5. Now, if it was a full tank, it would be from 0 to 5. But we're going from 1 to 5, and it's pi, which comes out, density, which comes out, and 2 meters squared, a constant, so that's 4 comes out, and the 9.8 due to gravity is a constant, so that comes out, and the only thing left in here is the x dx. So we integrate that. We get 1/2 x squared dx, evaluated from 1 to 5, times all these constants. And that would give you the work to move the water out of that tank. So there's a lot of physics in here. Now, the book will tend to go to, let's do the English system so we don't have to worry about getting all that physics. It makes the physics a little bit simpler. All right, I'm going to do the same problem again, but now I'm going to make a tank that's not cylindrical, but conical. Still 5 meters tall, still a radius of 2 meters at the top, but not at the bottom. Still filled to 4 meters. And so it's going to be density of water, I'll put that outside, 1,000, times the volume, which is going to be pi r squared, times the thickness of the slice, times how high I have to lift it, and that's again going to be x, and as this water goes down, x gets bigger, so it's going to be times x, so I should put the dx at the end, but I'm just trying to keep them together, and evaluate it from 1, so we're starting off lifting at 1, that's what x would be, and x will grow till it's 5. Now, what is r in this case? Well, r is changing as we go down the tank, so we have to come up with an equation for the r. Well, I believe we have some triangles here that we can make a ratio for. For example, r is to 2 as this, which is 5 minus x, is to the whole length 5. Or you could have written it 2 to 5 is r to this length, which is 5 minus x. These will give you both the same thing. We need to replace the r, so I'll multiply by 2, and then square all of that and put that here. Take it times x, and then find the antiderivative, and we'd find out how much work it takes to pump the water out of a cone. At least the work that required to lift the water to the top of the cone. Okay. Now here's another example of work. Let's say there's a building that's 50 meters tall, about 150, 160 feet, and they're working on the roof, and so the worker up here is trying to pull a bucket up on a rope. And let's say the bucket has 50 kilograms of mass, bucket and whatever's in it. Nails, hammer, tar for the roof, whatever's in there. Worker's got to pull it up. But the rope has some weight too, so at the beginning, the worker's lifting the rope and the bucket, and as they get up, the worker's lifting less of the rope, and there's a pile on the top of the roof, and so the force decreases as you work. So let's say that I give you that the mass of the rope is 0.1 kilograms per meter. So if there's 50 meters of rope, 50 times that means the rope is about 5 kilograms, which is about 10 pounds, 10.1 pounds. And that makes sense. A rope 50 meters, 150, 160 feet long would be about 10 pounds, maybe a little bit more if it's wet. Okay, so we have to find the integral of force times distance. So if I say x is how far up this bucket has been lifted, then we'd be integrating x from 0 to 50. The force would be density times the little bit that we lifted times dx, so that would get rid of the meters, times how far we have to lift it, and that is x. We're going to lift everything x, and we're going to do it in little chunks, little bits, and the little bit is going to cause a force times distance, and we got to lift the bucket. So the density times the length of the piece length of rope we're lifting, and plus the 50 kilograms. So this is going to be distance you're going to lift it times the mass for the length, gives you the mass of the rope plus the 50 kilograms. Let's write it out here. 50 kilograms is the mass of the bucket and its contents plus 0.1 kilograms per meter times the length that you lift it. That would be the length of the rope, excuse me. This is the mass of the rope that's still hanging over the edge. No, that's not. The mass of the rope is 50 minus x, minus how much you lifted it. This times 50 minus x. If I lifted x, that decreases the amount of rope times that. And if I lift it some more, that's that. Okay, so this, let's get this right. 50 kilogram bucket plus the density of the rope times how much rope is there, and if I've lifted it X, the rope that's out there is 50 minus X. So this times this plus that is the total mass that we're lifting. And if you take the mass times the acceleration due to gravity, you get the force. And the force to lift it some short distance, that's the force times the distance, will give you the work. And we're going to make it go, X go from 0 to 50. There's the right equation. Kind of messed up that one a little bit a couple times. This is similar to what it would be like if a ship had to figure out how much work it was to lift its anchor out of the ocean. And there you have a chain that has a much higher density than, say, a rope. But it would be the similar for how long the rope is and all that kind of stuff. Okay, so now let's go to some of the problems in the book. A, suppose that a heavy rope hangs over a cliff. The rope is 200 feet long. So now we're doing this in feet. I was doing metric. They want to do it in feet. So I'm going to get a clean piece of paper here. So we've got a cliff that's 200 feet. We got a rope hanging over it. They didn't even put a bucket on it. And it says its weight is 0.3 pounds per foot. So this is a sort of a density per foot. It's not a volume, but just how much per foot. Well, it's got consistent cross-sectional area, so therefore we can call it per foot because the cross-sectional area would give you some other dimensions and make the foot cube. But this is a weight and not a mass. So since it's a weight, we don't have to multiply by the acceleration due to gravity. This is a force divided by a distance. So we have to multiply the force, 0.3 pounds per foot. We have to take it times how many feet. Well, the rope is going to be 200 feet minus however much it's listed. So it's going to be 200 minus X. That's the length of the rope. And that'll be in feet. That'll cancel the feet. That'll give me the number of pounds. Pounds is a force. So all we have to do is multiply by the distance. And the distance that it moves up is going to be a small amount. After we move it up that small amount, the mass changes because we got a little less length out there. And then we'll take that times a small change. And then we'll have to adjust again and keep going through. So we're just going to add up all these little pieces by doing the integration here. And we're going to integrate for x going from there's no x to the x is 200. And that's the setup for A. Now if we have a heavy bucket in a 100-foot well, and as you lift it, it loses 0.1 pounds per foot. So we're not going to have to multiply by gravity. We're not doing that. But the rope is 0.1 pounds per foot. So we're lifting the whole rope. If we put X down here, is this rope? Yeah, a bucket of water. The bucket and water together are 40 pounds, so that's a force. But it's losing weight, so it's going to be minus 0.1 times how many feet there are out there. And that's going to be pounds, and so many pounds per foot times the amount of feet of rope that's out there. So this would be a force, pounds, times the distance that we lift it, and we're going to lift it from 0 to 100. And that would be the setup for that one. Lifting the bucket out of a well. Then they say, well, what if instead of this being the weight of the bucket, and notice in this problem they're ignoring the rope, they say, what if it's, this is not the density, but what if it's 25 plus 15 e to the minus 0.05 h, or x, the height that you've lifted it. Okay? Well, since if x was 0, e to the 0 would be 1 times 15 plus 25, that'd be 40. So it's starting off with the same initial, but then as it goes up, this becomes a small number, and a small fraction of 15 and 25 will make it less than the 40, and it'll just keep going down. So this will be the force times the distance, and that should give you the work for lifting it 100 feet out of the well. Okay. Then they talk about Hooke's law. And I don't know how many of you know of Hooke's law, but if you've got a spring, and if you just set it on the counter, it could have some gaps in it. And you could pick up you could start squeezing that spring, and it would be fairly easy at the beginning, but it gets harder and harder and harder as you push on it. And Hooke figured out that springs obey a law which says that relationship, the force required, is a linear relationship between that and how far that's compressed. So if it takes 10 pounds of force to compress it an inch, it's going to take 20 to go 2 inches and 30 to go to 3 inches, etc. That's Hooke's law. It's a linear relationship. Same idea if you were trying to stretch it. So they say the force required to get it to some position is a constant times x. That makes it linear. Plus a y-intercept, but the y-intercept is always 0 on these. Okay. So then they say, they give you the scenario that a spring we choose, measure in force in pounds, and the distance spring is compressed or stretched, is 5 pounds, extends it to extends it 4 inches or a third of a foot. If we want to do it foot pounds, we've got to change it to foot and use a third. So the force equals a constant times the distance is Hooke's law, and the force is 5 pounds. We'll make it go a third of a foot. To get the third off of the K, we'd multiply by 3, and we'd find that the spring constant is 15. Okay? So now, work done to extend the spring from its natural length to 1 foot beyond its natural length. So we're going to have the force, which is going to be 15x, times little distances that we're going to change it, add it up, and we want it to go from its natural position, which would be 0, to 1. You find the antiderivative of this and evaluate from 0 to 1, and you would find out how much work is done, because this is a force and that's the distance. Then they said, well, how would you figure it out if it was already stretch to 1 foot and you want to go to 1.5. Well, we can figure out from 0 to 1.5 and subtract from 0 to 1 from this answer. And so do the same this same integral here. Or you could just, instead of doing that, so you don't have to do the subtraction, you just say, let's go from 1 to 1.5 feet of the 15x dx, and do it that way. Okay. Then I told in class a story about a house I had that I had to install a sump pump. A sump pump. I had a house I bought in Roslyn. It was a fixer-upper, and so I fixed it up nice enough for me to live in, and then I ran into a lady who had kids, and so I needed to expand the house. So I decided to put a basement under it. And when I was digging out for the basement under the house, I got down 4 feet and hit water. And when I dug clear to 7 feet, the water level stayed the same. So I had to pump water out of there to actually make the floor and do all that. But the water would come back in, and I knew, and it would find a crack in the cement, and my basement would always be flooded. So under the concrete floor, I put some gravel, and then I made a hole with pipe, just made a cavity. And so the water would run into here. I put a sump pump in there, and it would pump the water clear up to the top of the basement wall and out and pump it away. It actually went into the storm sewer. So that's what I had to do. And that's what a sump pump is something to keep the water out. And so how this worked was the water would fill in, the pump would pump it out, then it would shut off, and then the water would gradually fill up, and then it would turn on and pump out, and it would do this automatically. Sold the house to a lady who didn't understand when I told her that there's a sump pump in the basement, and you got to check it, you got to keep the battery backup on it. The pump went out after several years. She called me up and said, my basement's flooded. What did you do? And I said, it wasn't me. You didn't pay attention to the sump pump. You have to keep the pump working, or your basement will flood. Okay, so they're making up a problem here with not a cylindrical hole like I made. They made it called a frustrum. It's a part of a cone, a tank like this. Now I want you to notice that they put a Y and X axis. They put X positive down here and Y positive over here. That's kind of a little strange. Normally it would be Y is positive this way and X this way. So they've rotated it 90 degrees. Now, we're not going to worry about that. They're taking a slice of water, and if I'm doing a slice, I won't do a delta X. I will do D of X. And we're going to have to pump it out, not just to the top, but clear over the basement wall, which they say up here is 9 feet. And they say that the diameter at the base is 1.5 feet, and so they put this point for here, since this is the x-axis, halfway over, or the radius is 0.75, and up here it says the radius is 3 feet, from a diameter is 3 feet, so half of it is 1.5 feet. So that explains those two. And they said the depth of this thing is 4 feet. So that's why it goes from 0 to 4 and 1.5 to 0.75. Okay? Now, let's see. How much work is required to empty the sump pump if it is initially full? So we're going to have it completely full. So we'll take a thin slice right at the top. We'll call it dx. But we'd have to take the density of water, and now they're doing this in feet and probably pounds. And so we need to know how many pounds per cubic foot water is. And you could Google it, but they have it in a problem further down here. It turns out that it's in figure, in the one that's related to 643 down here in B, it says it's 62.4 pounds per cubic foot. So 62.4 pounds, so that's a force, per cubic foot. That's feet to the third. So we're going to have to find the volume to cancel out the feet cube and get a force, which we want, force times a distance. So we have to know the volume of the water that we're going to lift out. And so it's going to be a piece of a cone, like it shows here, a disc that's dx thick. That's its height. And it's going to be an area of pi r squared. Well, it's this r. Well, that r changes, just like in the cone I had. And so we have to come up with a relationship. Now, we had it all the way down, but they don't. So we have to figure this out this way. The radius here, r, is actually in the y direction, so it's y, and it goes through this point and this point, so we have 2 points. We should be able to figure out the equation of the line. So y, or r, if you will, is mx plus b. The slope would be going from 1.5 to 0.75. That's a decrease in 0.75. In the change in x is 0 to 4, or 4. That's an increase of 4, so plus. X plus the y-intercept, and it hit the y-axis at 1.5. So in our formula, we have to do pi r squared, so we would do in here this quantity squared. So this would give you the volume of the disk times the pounds per volume, and the volumes would cancel, the feet cube would cancel, and we'd get the actual force of required to lift this water, and the distance we're going to lift it is going to be, we're starting right at the top, and so it would be 9, but then as the water goes down, this becomes the x to the disk, so it's going to be 9 plus x. This disk right here would have to be lifted, the x plus 9, this one down here would be lifted this x, which is greater, plus 9, so it's going to be that. And we're to do this from 0, the x is down nothing, start right at the top, and go until it's empty, which is at 4 meters. Or feet, 4 feet. So there's the formula. Let's clean this up a little bit. Let's not worry about the units. This feet cube would be canceled by the feet on this, the feet on the radius squared, and on the dx, the thickness. Those foot measurements would all cancel those foot measurement. This is a constant, would pull out, the pi would pull out, and we'd have 62.4 pi integral from 0 to 4 of this negative 0.75 over 4 x plus 1.5 squared dx and 9 plus x. So I'd have to take that times itself, then times this, then I could integrate it if I didn't have a calculator, and then take that answer, evaluate that from 0 to 4, and then take it times that. Or I could just type that times this in y1 and use my calculator to find the area under the curve from 0 to 4. The answer would be work, force, pounds, distance, feet, so it'd be foot-pounds of work. Okay. And then we got a little bit further in class. We did consider a vertical tank of cylindrical tank of radius 2 and depth of 6 meters and filled with water of mass density of 1,000 kilograms per meter cubed and 1 meter from the top up to 1 meter from the top, and we got to pump it over the top of the tank. Well, this is just like the one I did on Friday. It's just a little different numbers, and so we have to take the density, 1,000 kilograms per meter cubed, times the volume. The slice will be pi radius squared times the height of that slice, which is dx, and we're going to lift it x, and x is going to go, since we don't have to start at the top, it's going to start with, after it's 1 down, and work its way up to 6 down. So you would take the x and put it inside, take all these constants, pull outside, and you'd have the integral of x dx, which is pretty simple. Then they say, consider a hemispherical tank. And they did not say which way this tank sits. Is it a hemisphere that sits this way, or this way, or this way? We don't know. So that was a problem with this problem. They didn't give us the orientation. So in class, we assumed it was a bowl shape. So we're going to go with bowl shape, and the radius of this bowl is, since it's a sphere, is 10 feet. And suppose that the tank is full to a depth of 7 feet. So the depth of the tank, if it's this way, would be the 7 feet. And that's the water line. And let's see, 7 feet. And they're telling us the water density is 62.4 per cubic foot. 5. And now the water is going to be pumped above the top of the tank 5 feet higher to a truck. So it's got to go an additional 5 feet taller. So if we put the coordinates like they did on the last one, y plus over here, x plus down here, we can call this x, the distance down to that water, which is going to start off at, well, if it's 10-foot total depth and there's 7 water in it already, that means this x is 3 where there's not water. So it's going to take the density of water, 62.4, times the volume of the water, the slice, which is going to be pi r squared, times the thickness, dx, and then how far we have to lift it. So that's volume times pounds per volume, so this would be a force, just pounds, the volumes cancel the volume units, times the distance, and the distance we're lifting it is x plus 5 more, And we're going to add these up as x goes from, think about it, if it's 7 foot is the top of the water and the tank is 10 foot total possible depth, x would start off with 3 and end up going to, well, if we emptied it, it'd be 3 to 7, 3 to 10, but we're only drawing it out so that there's, where is it? Suppose the tank is full, has 7 feet of water, and the top 5 feet of water is pumped out. So we're going to take 5 feet of water out, which is going to leave 2. So we're going to integrate. X is going to start at 3 and end up down here at 2 from the bottom, which is 8 from the top, and that's where we made our coordinate system. Now we have an R in here, so we have to get rid of the R, and that's not the radius of the whole tank, that's just radius of this slice that we're doing that's dx thick. So what's the radius there? Now to get that, we have to know that a sphere is a circle shape, and the formula for a circle is x squared plus y squared equals r squared. Our r for the sphere is 10 feet, and we have to square that, which makes 100 square feet. And x is this distance, and y is this distance, because that's in the y direction. And we need y squared, because r is y squared, so we have to solve for y squared, which is x squared minus the big radius squared, which is 100. So it's x squared plus y squared. We want y squared, so r squared is y squared, and y squared is 100 minus x squared. So our integral would change to the 62.4 would pull out, it's a constant, pi would pull out, and we'd have r squared times, x plus 5, so we'd have this squared that's y squared. No, y squared is r squared, so we'd have that, just that, 62.4 times pi times the y squared times dx times x minus 5, or x plus 5, so I'm going to put the x plus 5, so it looks like it's in part of the integral, and so I'd have to multiply this out, FOIL it, integrate it, from 3 to 8, and I should get the work to lift the water that's 3 feet down before you get to it, and we can pump it out to 8 feet down and lift it all also up that 5 feet. Okay, now the part that I didn't get to in class that I'm going to talk about now. Pressure. As you go deeper into, say, water, if you happen to be a swimmer down in a lake, the amount of water sitting on top of you determines the pressure. So the deeper you go, there's more water on top of you pushing down, and that increases the pressure. So the pressure varies as you go up and down. So if you have a dam, the pressure is going to be the most on the bottom of the dam and not so much at the top of the dam. So if there's holes in the dam and you have to put your finger in it, like the Dutch boy, you would want to be doing your finger in the top part, not the bottom, because it's a lot more pressure in the bottom. It'd be harder to hold it. Okay. So, they're suggesting that we consider having a dam that's a consider a trapezoidal shaped dam that is 60 feet wide at its base and 90 feet wide at the top. 60 feet, 90 feet, and assume that the dam is 25 feet tall, with the water rises to within 5 feet of the top. So this is 20 feet. And so they want to know how much force is exerted against the dam. Well, the force won't be as much up here as it is down at the... So I took a pause here to check and make sure I was doing this correctly. Yes, the pressure is 662.4 pounds per cubic foot. That's how much water weighs. So if you're down, say, 10 feet, you've got all this water sitting on top of you, which makes the pressure 10 times this. So 624 pounds of pressure per square foot. Because we're taking the 62.4 pounds per cubic foot times the depth, which is in feet, and so that gets it down to an area. And so we're getting the pressure on the dam at that depth at the area based on the area of the dam. So we then have to take a slice of the surface of the dam that's against the water, which will make it dx high, and it'll be the length of the dam across. So we're going to have this length, L, times dx, that's the area, times 62.4 times the depth. And now we've got, that's the pressure, the force times the depth makes the pressure times the area, and we're going to add up the pressure for all the way down from, it started from 5 feet from the top down to the bottom. And so that's going to be, if the dam's 25 feet tall, we're going to go from 5 to 25. Except, the depth of the water wouldn't be x then, because x would be from the top of the dam, and the top of the water is down 5, so we'd have to go x minus 5, so that when we put in 5, we're at the surface, we have no depth. And then as we go deeper, we get to the depth of the water is 25 minus 5, so we have to use x minus 5 for how deep this slice is in the water. That's what we want. How deep the slice is in the water, how many, the pressure, that times the length. And the one other thing that we have to take care of is the L. And if this is going from 90 to 60, we have to come up with a linear relationship. Let's see, so 90 to 60 is a decrease in of, 90 to 60 is a decrease, a change of 30. So I should go 60 minus 90 because it's a decrease. So it's minus 30. This is going to be a linear relationship, so I'm getting a slope. The change in the length is 30 for the 25 feet. So if we take that times the depth, and then start with the y-intercept of the full length, 90, I think that'll work. So that when we go from, when x is 0, we will get the width to be 90, or the length to be 90, and when x is 25, we're going to get 30 divided by 25 times 25, which is negative 30, plus 90 is 60, which is the length there. So this will give us the right length at x from the top of the dam. So to do this problem, it'd be from 5 to 25, 62.4 times x minus 5, because we're starting down 5, and the length will be, based on this equation, minus 30 over 25 x plus 90, and the dx is the height of that area. And so we'd have to take the x times this term, x times that term, minus 5 times this, and minus 5 times that to get it. And they do some more with just water density. So let's assume it's 100 feet wide and 50 feet tall, and it's a rectangular dam. It's not this one. Rectangular dam, 100 feet wide, 50 feet tall, and suppose the water presses the dam all the way to the top. So the dam's filled to the top. So the slice, the area of that would be, let's call it dx, and it's down x, and the pressure would be 62.4 times its depth times the area on the dam, which is going to be 100 dx, and add that up as x goes from the very top to the very bottom, and that would be the pressure on that. Then they say, consider a semicircular dam with a radius of 30 feet. Suppose that the water rises within 10 feet of the top. And I'm not going to do that one because I'm not sure whether they're talking semicircular dam like this or like this. Like you see some dams that are cupped like this, like Hoover Dam, but then they don't say whether it's straight up and down, and I'm not sure what they mean by that. Then they ask us to do this one, so we'll do that one. Consider a trough with triangular ends as pictured in the figure, where the tank is 10 feet long, so this must be 10 feet. Top is 5 feet wide. And filled to 4 feet deep. And full to within a foot of the top. And we have the density of water. How much force does the water exert on one of the triangular ends? So, if we call x right at the top 0, the water's down 1, so it's going to be an integral from x being 1 to the bottom, which will be 4. 62.4 times the width of the slice, which is going to change, or times the depth, which is going to be the depth of the water at the slice is going to be x minus 1, because it's 1 off of the top. And then now we have to do the slice, which is, that's y, so it's 2y times dx. And so we've got the density of the water times how deep the water is at the x level. And the water is 0 at 1 and 4 feet deep. Oh, we're going at 3 feet deep at down here at the bottom of the tank. dx. Okay, that would be the pressure. So we would do we got to get rid of the y. And the y, it would be from here to there. And we could set up, we could do triangular ratios here. Y to, this is x, so this is 5 minus x. No, 4 minus x. The tank is 4. Was it 4 or 5? Got to get back here. 5 feet wide, 4 feet deep, so it's 4 minus x. That's how much this is. So we could say y is to 4 minus x, this to this, as 5 is to 4. And so y would be 5 fourths times 4 minus x. And then we double that, so it would be 5 halves times 4 minus x dx times x minus 1, integral from 1 to 4 of 62.4. And we'd work that out.